A comet can be a wonder to behold. For thousands of years, these visitors have mystified, enchanted, and terrified humanity. And even today, despite much attention from astronomers, the popular science of comets is filled with enigmas and unresolved mysteries. Two theoretical views of comets today stand in stark contrast. But aided by recent discoveries, we can compare the two vantage points and test them against presently known facts. It was only in the mid-20th century that a scientific consensus emerged on the nature of comets. In 1950, astronomer Fred Whipple proposed a model that came to be known as the dirty snowball hypothesis. Whipple envisioned comets as conglomerates of frozen gases, mainly water, carbon monoxide, and carbon dioxide, together with the primordial dust of the early solar system. But a dilemma had to be solved. Comets lose considerable material at each pass around the Sun. This means that the comets we see cannot have been around all that long. So the Dutch astronomer Jan Oort envisioned a vast horde of icy objects circling the Sun about 1,000 times more distant than remote Pluto. He imagined that after billions of years, one of these dirty snowballs could be deflected from the icy cloud by a passing star. It might then fall into the inner solar system to produce an active comet. As astronomers came to accept the idea, they called this theoretical source of comets the Oort cloud. But in the early 1990s, with improved observations, it became clear that numerous objects circle the Sun at much closer distances than the conjectured Oort cloud. And eventually, all short-term comets were theorized to have arrived from a disk of debris called the Kuiper belt, extending out from Neptune's orbit and containing objects that drifted inward from the Oort cloud across the eons. By astronomers' own admissions, these theoretical guesses leave numerous comet mysteries unresolved. But always it is assumed that comets are composed of dust and ice warmed by the Sun to create a coma and tail, leaving a rind of dust. The theory suggests that beneath the blackened, shallow crust, pockets of gas form. At critical moments, the pressure breaks through the surface, creating jets blasting vapor and dust away from the nucleus. But how well does this popular theory explain what we've more recently learned about comets? In an alternative view, comets have a much different history. This view sees comets as debris left by intense electrical activity in an earlier phase of solar system evolution, not billions of years ago, but a much more recent epoch of planetary instability and violence, one that reached even into early human times. This new perspective combines historical facts with surprising recent discoveries about comets. In the electrical interpretation, not just comets, but asteroids and meteors as well, were born in planetary upheaval, as electric arcs blasted material from the surfaces of planets and moons to produce fused formations identical in appearance to fused material in laboratory experiments with electric discharge. Here, an arriving comet moves on an elliptical path through the Sun's electric field, an exceedingly weak field, but immensely powerful across the great distances of interplanetary space. As the comet draws closer to the Sun, the charge imbalance triggers electric discharge, creating a coma and long cometary tail. The mysterious jets of comets can then be understood in terms of arc discharges to the nucleus, very similar to industrial electric discharge machining. The excavated material is accelerated into space along the jet's filamentary pathways. Intermittent and wandering arcs erode the surface and burn it black, leaving the distinctive scarring patterns of comet nuclei. The jets explode from the nucleus at supersonic speed and retain their coherent structure for hundreds of thousands of miles. Seen in terms of an electrically neutral vacuum in space, nothing of this sort should occur. The tails of comets reveal well-defined, twisting filaments extending up to tens of millions of miles without dissipating in the vacuum of space. For proponents of the electric model, this contradiction of neutral gas behavior is no surprise. It is the testament to the comet's electrified environment. The proponents of this interpretation also say it's the electric force that holds the spherical coma in place against the solar wind as the comet races around the Sun. The diameter of the visible coma will often reach millions of miles, and it's surrounded by an even larger and more improbable spherical envelope of fluorescing hydrogen, visible in ultraviolet light. For decades, we've been assured that comets were made in the deepest of deep freezes in interstellar space. Comets coalesced from interstellar stardust, the primal material of the universe, before the emergence of the Sun as we know it, or its planets and their moons. A foundational principle of comet theory and of modern cosmology as a whole is compositional zoning. At the outermost reaches of the Sun's domain, formative processes were limited to the most rudimentary material, raw dust constituted in an environment close to absolute zero, with no complex chemistry. In contrast, bodies later formed close to the emerging Sun would exhibit minerals formed at relatively high temperatures. For decades, this theoretical claim stood fast, and the claim was even carried into space. It's what prompted the Stardust mission to Comet Wild 2. As indicated by the very name of the scientific mission, the theory required that a comet be constituted of stardust. But the core assumptions of comet theory could not withstand the shock from the data returned by the Stardust mission. Launched on February 7, 1999, Stardust carried with it a tray of aerogel to capture samples of comet dust from Wild 2, and it returned these samples to Earth. Scientists could then view microscopically the raw material of a comet. The first surprise was the size of the dust grains, much larger, stronger, with far more complex structure and chemistry than theory allowed. And the gel did capture trivial amounts of the expected microscopic dust, invisible to the naked eye and leaving shallow, bowl-shaped pits in the aerogel. But more common by far were much deeper tracks, more in the shape of carrots than shallow pits. The particles themselves were clearly visible to the naked eye. To their amazement, the mission scientists found elaborately developed crystalline structures in the Wild 2 dust. It was an exciting discovery, but one that challenged all prior theory of a comet's origins. Crystalline structures cannot form in the absence of minimum temperatures, temperatures unavailable in interstellar space. The spectra of silicates in cometary comas were evident as far back as the probes of Comet Halley, though largely ignored. But the mystery couldn't be ignored after arrival of the comet Hale-Bopp in 1997. This comet's spectra placed an exclamation point on crystalline silicate structures in cometary comas. To get past the problem, astronomers hedged their bets. They surmised that billions of years ago, the raw material of the comet was ever so slightly warmed by an emerging sun. Then all of the discrete particles in a vast circle around the sun were transported outward by means only guessed at to the faraway and frigid Oort cloud. But this rationalization failed outright once the scientists had real comet dust in their laboratories. The grains were simply too large, and the mineralogical and chemical compositions far too complex. One puzzle was followed by another. Comet theory assumed that water ice was a primary constituent of active comets. But no water ice was detected on the nucleus of Wild 2, and not a trace of water was found in the well-preserved comet dust. And yet, paradoxically, the raw comet material of Wild 2 contained iron and sulfur minerals that can only be formed in the presence of liquid water. Liquid water, not in the near-perfect vacuum of deep space and not in a deep freeze. Instead of trivial warming, the Wild 2 minerals revealed a diversity of formative processes. Various sulfide minerals requiring liquid water can only exist below 210 degrees Celsius or 410 degrees Fahrenheit. These minerals have never seen higher temperatures. But also occurring in the comet dust was the mineral olivine, whose molecular structure rapidly breaks down in the very presence of water. It's a common igneous form, an abundant byproduct of volcanism. Perhaps the biggest surprise was that some of the comet minerals, such as forsterite, in the instant of their formation, were heated to thousands of degrees. Forsterite is formed in the most intense volcanic heating of silicates, but occurs also in lightning strikes to silicate rocks. The message could not have been more emphatic. It was not just the hypothesized Oort cloud that failed to work as advertised. The entire concept of compositional zoning, as applied to comets, failed its first acid test. Comet material requiring moderate temperatures in liquid water. Comet material formed at exceedingly high temperatures. Only the most trivial levels of the presumed raw material of comets, interstellar dust. A complete absence of water, despite cometary material originally formed in liquid water, though the olivine abundances could not have been formed or even survived in the presence of liquid water. And of course, liquid water requires atmospheric or other pressure. It cannot exist in the extreme vacuum of interstellar space. To this seemingly contradictory picture, we must add extreme selective heating. Selective heating because much of the compositional material could not survive the superheating that created olivine, forsterite, and other crystalline minerals. The Wild 2 discoveries have forced upon comet science one inescapable fact. In our own cosmic neighborhood, the diverse mineral content of Wild 2 is typical only of planets in the habitable zone of a fully developed sun. When the fundamentals of a theory are falsified by unexpected findings, a new vantage point is required, one that explains and predicts the surprises without introducing new contradictions. The conjectured Oort cloud freezer, forming and preserving comets for billions of years, is falsified by the Wild 2 findings. Only the diverse surface environments of rocky planets can provide the required raw material, and only the recent formation of comets can explain why these rapidly degraded objects are still with us. The bold question must now be asked: were comets created in recent periods of planetary instability and intense electrical events? Would minerals formed in liquid water then come as a surprise? Would comets now exhibiting no water be a surprise? Or crystalline structures suggesting igneous processes, or minerals pointing to the exceedingly high temperatures of lightning? A more unified picture of comet formation is available to us. And if comets were born electrically, what might the causative connection be to asteroids and meteorites, the apparent cousins of the comet? The Wild 2 mineral cubonite, a copper iron sulfide, is abundant on Earth and so too on Mars. In fact, it's found in Martian meteorites now known to have been blasted up to escape velocity from the surface of Mars, later to arrive at Earth. A few years ago, things now stated by astronomers would have been considered preposterous. Astronomers now acknowledge that the Martian moon Phobos, long called a captured asteroid, was formed out of material blasted from the Martian surface. For the source of a comet's constituent materials, planets close to the Sun's habitable zone are the most reasonable places to look. The foremost candidate is the planet Mars. In this intellectual adventure, we must revisit all earlier ideas about solar system history. Evidence for high-energy electrical events can no longer be ignored. The popular billion-year scenarios describing a comet's origins will be displaced by things now established as fact. And the changing picture of solar system history will surely not stop at the new story of the comet. Pluto. He imagined that after billions of years, one of these dirty snowballs could be deflected from the icy cloud by a passing star. It might then fall into the inner solar system to produce an active comet. As astronomers came to accept the idea, they called this theoretical source of comets the Oort cloud. But in the early 1990s, with improved observations, it became clear that numerous objects circle the Sun at much closer distances than the conjectured Oort cloud. and eventually all short-term comets were theorized to have arrived from a disk of debris called the Kuiper Belt, extending out from Neptune's orbit and containing objects that drifted inward from the Oort cloud across the eons. By astronomers' own admissions, these theoretical guesses leave numerous comet mysteries unresolved. But always it is assumed that comets are composed of dust and ice warmed by the sun to create a coma and tail, leaving a rind of dust. The theory suggests that beneath the blackened, shallow crust, pockets a comet can be a wonder to behold. For thousands of years, these visitors have mystified, enchanted, and terrified humanity. And even today, despite much attention from astronomers, all hypothesis. Whipple envisioned comets as conglomerates of frozen gases, mainly water, carbon monoxide, and carbon dioxide, together with the primordial dust of the early solar system. But a dilemma had to be solved. Comets lose considerable material at each pass around the sun. This means that the comets we see cannot have been around all that long. So the Dutch astronomer Jan Oort envisioned a vast horde of icy objects circling the sun about 1,000 times more distant than remote Pluton's. The popular science of comets is filled with enigmas and unresolved mysteries. Two theoretical views of comets today stand in stark contrast. But aided by recent discoveries, we can compare the two vantage points and test them against presently known facts. It was only in the mid-20th century that a scientific consensus emerged on the nature of comets. In 1950, astronomer Fred Whipple proposed a model that came to be known as the dirty snowball